Hey, what's up everybody? So I didn't have time to finish the problem in Recitation today, and I said that I'd put a video up, so I'm going to do that here. I'm not going to do the whole problem because I feel like that might take quite a while, but I want to at least like get you started so you can kind of see what you would have to do for the other part. Basically two parts, right? Like, so remember that this was essentially the setup. Let me resize this real quick. It's a bit big. I don't know, 80% maybe. So what we had was we had our x and y axes, and we had some point charge at AB. So what we would do, right, is we would write something like this. I'll do that down here. Hello? Okay. So problem statement, we'll just write it out. Find the electric field, and I'm gonna say vector, right, because finding the magnitude is a bit easier, but to find the electric field vector, we have to find both the magnitude and the direction, right? And so throughout this class, you're going to be very mindful of like things that are vectors and things that are scalars. And you know, we'll definitely talk more about that later. But this is what we want, right? We want to find the electric field vector at point P. I wrote a fancy P, we'll do that. P on the y-axis, right? So what I want to do is I definitely want to talk about the different notations, right, for R, because there was a lot of R's floating around on the board earlier, and I think that this could be potentially confusing for some people, and I want to make sure everybody's clear on it, right? So we'll go through that as we solve the problem. Let's just say if Q1 equals 2E, I think that was the number that I said, right? It just double the electron charge. Remember that E, even though its electron charge is positive, right? It's a constant. So if we wanted to make sure that it was interpreted to be negative, we would have to put a minus sign in front here. But I mean for this to be a positive charge, right? So we're just going to leave it with an implicit plus sign here. And let's say is located at, and then here's where we're going to see the R prime thing, right? I'm going to write R prime equals A comma B, right? Just an ordered pair to specify where this is. And this is a vector, right? So whenever I type a vector, I am just going to make it unitalicized and bold, because I think there's no circumstance in which you should ever type a vector and put an arrow over it. That's just gross. So that's going to be my convention, right? I'm going to stick to that throughout the whole semester. So just, you know, be mindful of that, right? It might be different from the textbook or from what the professor does, but this is my thing, and I think it's the best. Okay, so the idea is that this R prime is going to tell us the position of the source charge, right? Remember, this Q1 is a source charge because it's generating, or it's the source of an electric field that is, you know, located at P. Now, I mean, the electric field is technically everywhere due to this charge. Like there's an electric field, say, here and here and here and here, wherever you could really put a point down, right? But we're concerned with this. So in this case, this R prime, right, again, just to stress this, is meant to be the vector that takes us from the origin to where the source charge is, okay? Now, in this case, let me just put some words down here. What we want, right, is we want to figure out what the electric field is at some point on the y-axis. And, you know, I've drawn it in to be above B, but it doesn't necessarily have to be, right? But we'll just kind of pretend that it is above B. So if B is, you know, like 2 nanometers, and P would be like 4 or something maybe, right? But I forget what I was going to say. I think it was about the R, right? So the R with no prime, this is the vector that takes us from the origin to where we want to calculate the field, right? So this will just leave general. We'll call it 0 for the x component and y for the y component, right? So what we have to do then is we have to do a few different things here, right? We have to probably first make a sketch, because that's always a good idea. And so let's just get that out of the way. I'm not gonna like do it live because that would be annoying for me, but I've prepared a sketch. So what I'm gonna do is I'm gonna delete this image, and then I'm gonna basically bring in the same image, but with the sketch. All right, so give me a second here. Just delete that. I have this ready to go. It's rather big. Not surprisingly, let me just adjust the size here. Take it down to like 70%. Okay, so this is my sketch. I'm gonna make it even smaller. Take it down to like 50. And I think you guys should be able to see what's going on here, even if it is a little too small, because you just saw the previous image, right? So all I did, right, was I just took I just drew a dashed line from Q1 to where I want the field. And now I have the electric field, that's pointing up and to the left, right? Because the electric field, due to a positive point charge, is going to point radially away from the charge. Whereas for a negative point charge, the electric field it generates is going to point toward the charge. And so remember that that's included in our electric field formula, which was something like this, right? K Q over R squared. And then I am going to, okay, don't hate me, but because it's hard for me to make a script R in equation editor, I'm going to use a big R, right? And we'll just all agree that this means the same thing as script R. So this is a vector. This should actually be big R squared too then. And this is going to be a unit vector, right? Because we want this to specify the direction, but we don't want it to affect the magnitude of this quantity here. So the unit vector is a perfectly natural thing to use. Now, remember what I was doing. I'll just, because I can't really type it, I'm just going to show you what I meant by the script R in case you don't remember or you were daydreaming, right, or whatever. It's totally fine. But remember that I was trying to draw something like this. It's just a cursive R, this vector. So instead of using this for the duration of the video, I'm going to use capital R, but they mean the same thing, right? So anyway, we want to recall what this was defined to be. So remember that it's going to be just R minus R prime, right? So what we have here is, I'm just going to make these into vectors. Not that. There we go. And we can directly calculate this, right? We can just write, for instance, that this is vector subtraction, right? So we just subtract the components separately. So what I would put here in the first position, right, is 0 minus a, and then in the second position I am going to put y minus b, right? And of course 0 minus a is just negative a, so let's write it like that. And then y minus b unfortunately doesn't clean up any more than it's already been written, right? So these are the components of the vector, and we want to probably make sure that they point in the same direction as we expect the electric field to, right? So how do we do this? Well, we don't have any numbers, right? But I should tell you that whenever I write like A, B, C, D, whatever, these are going to be taken to be positive, right? So A is some positive number, B is some positive number, with dimensions, right? Dimensions of length. And so what we can see from this R vector, right, the separation vector, remember, is that it has a negative X component, right? As does our electric field. So that's probably good, right? And then we're saying that Y is larger than B just for purposes of definiteness, right? So then Y minus B is also a positive number, which means that this has a positive Y component. So just like a very quick check, right? We expect this electric field to have a negative X component, which it does. and then a positive y component. So this is good, right? This looks good. So this is our r vector. Now, what we really want though is we want r hat, right? Because that is the vector that tells us the direction. And that's one of the things in our formula, right? So let's go through and essentially what this is going to come down to is just figuring out what big R squared is and what big R hat is, right? So we'll start with big R squared because I think that's easy. So I'm just going to say from the Pythagorean theorem, right, we have, oops, why did that just disappear? Okay, let me try that again from the Pythagorean theorem. We have, and, you know, we can do this with vectors, right? Hopefully everybody's aware of this, but maybe it's been a while, maybe you had a crazy winter break, right? No judgment, but we can just write that essentially big R is the hypotenuse of the right triangle with one side length A and the other side length y minus b, right? So what this works out to be is r squared equals, and I'm going to be very pedantic here, I'm going to put negative a quantity squared, right? Even though it doesn't matter because, you know, any real negative number squared is positive, right? And then y minus b quantity squared. And so this, of course, is just a squared, right? Plus y minus b quantity squared. And that's one part, right? We're effectively halfway there because we figured out what this is down here. And you know, what's funny is that you're probably very tempted in a situation like this to take the square root because that's just what you've been trained to do. But you don't have to, right? Because we actually want r squared. That's what the formula uses. So, you know, this is fine as is, right? Now, r hat is a little trickier, and I'm going to go on a little bit of a tangent here about vectors and unit vectors, because this is important and definitely one of the things that Dr. Hong wants to stress this semester is the math, right? So we're going to talk about this a bit. And what we're going to say is that, I'll just say, recall that a unit vector must have magnitude 1, right? So we mentioned that a little bit before, and I said something like, well, this is a unit vector because we don't want it to affect the magnitude here, right? We don't want it to have some non-1 numerical value. So we're just going to keep it that way by, you know, ensuring that we turn this R vector into, this big R vector into a unit vector. So I should say for any arbitrary vector, we can write something like this. Let's just call it v. We could write v equals vv, and I'm going to fix this up, right, because this looks stupid. But now on the left-hand side here, we have a proper vector, right? This is the magnitude, and so that's another notational thing. Whenever I write, or whenever I type vectors, I'm going to make sure that the vector itself is unitalicized and in bold, but the magnitude is going to be italicized and not bold, right? And then I have to turn this into a unit vector, like that. So this looks kind of stupid. Actually, I think I like the hair space in there. Don't mind me. I have problems. So this looks kind of stupid, but it's true, right? Because all we're saying is that v is some vector that has magnitude v and points in the direction of v. That's it, right? So this looks weird, but it's true, and it's actually kind of useful, because what this allows us to do then is this allows us to solve for v hat. And I'm going to have to go through and format this again, right? It's hard to do very quickly, but so this is going to be v hat on the left here that we're solving for, right? This is v on top. I can still do basic algebra, I think, right? And down here is the magnitude. So this is good. And this is our blueprint for solving for something like big R hat here, right? So I will say then that this means, and then we're going to write out, I'm going to try to do this from memory. I'm going to say that r hat, and this will probably be a disaster, but it's okay, right? Is just going to be r over r. Now this is r, the vector, and this is the magnitude of r, right? And so I'll switch up the notation a little bit here, just to expose you to, you know, the different kinds of notation that we're going to see. But this r vector we already found, right? It's the separation vector. It has, you know, negative a for an x component and y minus b for its y component. So I'm going to write negative a and then hello. Okay, that is fine. X hat, right? Because we're using unit vectors now. And then plus, and it should be y minus b. These should not be in bold, right? Y hat. Like this. So this is our r vector, just expressed a different way. We already knew this, right? Because we already solved for it. And then down here, we just write out the square root, and, you know, before we were thinking about r squared, right? So we didn't take the square root, but now we're going to have to take the square root, right? This is going to be square root of a squared plus y minus b quantity squared, right? And we could separate this out if we wanted to. We could just write like negative a over the square root of a squared plus y minus b quantity squared, and this is x hat, right? Like so, and then plus y minus b over the same thing, right? Square root of a squared plus y minus b quantity squared y hat. Right? So this is what it is. This is our unit vector. And, you know, we want to make sure that this has magnitude 1 when it comes down to it, right? And so how do we check that it has magnitude 1? Well, we apply the Pythagorean theorem again, right? So what we could do is we could use Mathematica here, and I'll just show you how you could do this, right? Just as a little bit of exposure to Mathematica, because it is really a very useful, powerful piece of software. And so I can do something like this. This might be a little confusing, but we really just want to think about how we can do this as simply as possible, right? So what I'm going to do is I'm just going to write u squared plus, and I want to say v, but I'm not going to because we have, no, we don't have v, it's fine. So this v is just a dummy variable. It's not the same as the vector we were just thinking about, which we never really even gave, you know, any quantitative values, but you'll see what I mean, I think, in a second here. So let's take the square root of this, actually. So I'm going to write out this square root of u squared plus v squared, right? And I'm going to hit shift enter, and that just gives me what I expect. So now what I'm going to do, and this is the part where I'm going to make things a little bit easier on myself, I'm going to have Mathematica substitute in the x component as u and the y component as v. So what I do is I write, oh god, I don't say this often, I do it all the time, but I think it's %/dot, then open curly brace, right? And it kind of does this annoying thing where it gives you the closed one. I don't like that, some people might like it. But what I'm going to do is I'm going to say, hey, Mathematica, I just, you know, do a hyphen and then a greater than symbol, and it makes it an arrow. I'm going to say, hey, Mathematica, u is actually this, right? Square root of a squared. No, I wasn't having a stroke. I'm fine. I know you guys are very concerned about me. I'm going to say, hey, Mathematica, u is negative a over the square root of a squared plus y minus b quantity squared, right? So now it's going to plug this in when I tell it to, and then I have it do the same thing for v, right? I'm going to tell it now v is y minus b over the square root of a squared plus y minus b quantity squared, and then I have to do the closed curly brace, right? I think this looks good. And what do we expect it to spit back at us, right? That's the question. And I mean, I think that based on the discussion we've had, we definitely expect it to give us the number 1 back, right? And let's just confirm that it does that. And so it gives me this. And so if I say something like, how do I make it realize that this is, oh, it shouldn't be too hard. I think if I just put full simplify, it'll do it. And it tells me it's 1, which is great because that's what we expected, right? So, yeah, we have successfully found the unit vector, right? And, you know, you don't have to do it this way, right? You could always do it more in terms of like cosine and sine, right? And that is perfectly equivalent. But what you would have to do it that way is you would have to figure out what this angle is that say is made by this right triangle with base that passes through B and Q1, right? So imagine there's a horizontal line here. What is the angle that the electric field vector makes with that horizontal line? That's perfectly fine, right? But this is, I think, better in some ways, even though it might not look better, and something you should be comfortable doing in a perfect world. Okay, so then, you know, we're almost there. We just have to kind of take it home. And so what I'm going to do is I'm going to say that, remember we wrote that E equals K Q1 over big R squared in the R hat direction. And let me just fix these and make these into vectors. And unit vectors, right? So that, and then we have that... Let's see, we said that Q1 is 2E, right? R squared, big R squared, we found to be this. So I'm just going to copy and paste it. And then we have to tack on the unit vector that we found, right? Which is this. Like so. And this is kind of gross, right? I mean, I'm not going to lie to you. This doesn't look that pretty. But the nice thing is now that you've basically solved this problem for the case that like your point charge is in the first quadrant, right? So A and B could be really any numerical values. And then you now know what the electric field is at every point on the y-axis, right? If you could just, you know, crank this out with some numerical values. You can clean it up a tiny bit, right? So maybe we just try that real quick before we end. But what you can do, right, is you can first of all obviously write that this is 2ke. That's, you know, just the typical thing to put the number out in front. But then, you know, you wanna note probably that this term down here, a squared plus y minus b quantity squared, is technically this whole expression in parentheses also to the first power, right? Now these down here, I struggle with powers, so I'm actually gonna write this out mostly for myself, but hopefully some of you appreciate this as well. We could write something like this then, because remember a square root is basically the 1/2 power. So I could write a squared plus y minus b quantity squared, then take this whole thing to the 1/2, and then do the same thing for the other denominator, like so. And then I could distribute this term out in front, right? Because this is just some number to the first power, right? and this is just some number, the same number to the 1/2 power, and you know, algebraically can combine powers, right? Not an issue at all there. And that will clean it up a little bit, because what you can do actually is I'll just do it. Even though me doing algebra is dangerous, but it should only require one more line. So what I'm going to do here is I'm going to factor out the denominators, and I'm going to keep 2ke on top. But then what this becomes is a squared plus y minus b quantity squared to the 3/2, right? Because 1 plus 1/2 is 3/2, and that's our rule for combining powers, right? In this way, by multiplication. And then what we could do is we could make this look a bit better. We could write negative a x hat, and I'm gonna change this quickly, plus, and then y minus b y hat. And so this is a little better. I hope we all agree that it's at least a little bit better. And this would be as much really as we could simplify this. And you know, you're gonna want to go through, make sure I didn't make any algebra mistakes, because as I've mentioned several times now, I'm not good at algebra. I mean, I'm good at algebra. It's just that when I'm doing it on a computer, and there's also the added pressure of being recorded, then, you know, things can get a little crazy. But you're going to want to check the algebra. But this process that we used here is 100% correct. And, you know, something that I hope everybody feels comfortable doing, or will soon feel comfortable doing. Now, before I wrap up, I'm going to just talk about like the actual problem that I gave, right? Which was the same thing, except there was some charge over here on the other side of the y-axis, right? So what we would do in that case, and I just noticed that I called this E1, but I've been writing just E all along, so just interpret this as E1. Anyway, so let's talk about the actual problem that we were trying to do, which was this, but there was another charge over here, a negative charge on the other side of the y-axis, and there wasn't really any symmetry that we could exploit, right? Because, you know, symmetries are things you want to look out for, because they can often simplify your calculations greatly, and we'll talk, you know, much more about that later. But there wasn't any obvious symmetry, because, you know, it wasn't like the other charge was at negative a negative b, or rather negative a positive b, right? Because we would, you know, maybe want it like here. But I guess technically negative a negative b would also be a symmetry. But anyway, what we would do then is we would just repeat the exact same procedure for Q2, right? To get E2, we would do all the same stuff, and then we would just take the vector sum of E1 and E2, right? Because the superposition principle tells us that we can combine these things, speaking good vector, right? As one of my former professors used to say. So that means, right, like we just have to go through and very carefully calculate what the other electric field is due to Q2, and then just take the vector sum at the end, right? So hopefully you don't find it too difficult. Yes, it's tedious, right? But, you know, it's good for you, I think. And hopefully something you feel good about being able to do, right? So that's it for this video. Hopefully you find it helpful, and I will catch you in the next one.